So good morning, everyone. So before I start today's class, there is a question on the chat window. So question says that when time quanta decreases, then we say that response time decreases and turnaround time increases. So does this always happens or there can be exceptions? So I think we made this statement in the context of round robin scheduling algorithm. In the round robin scheduling algorithm, when the time quanta decreases basically, then this will always happen, these two things, because the response time will decrease because now the processes will get response quickly because switching will happen too often, and so the any waiting process will get the response faster than when the time quanta was larger. And also the turnaround time will also tends to increase because now each process will stretch as long as possible, because even if there so because when shorter times is there, the process will tend to stretch till the end basically. So the final finishing time for every process will be larger than what it would be if the time quanta was less. So this will always happen I think in case of the round robin algorithm. uh, I can't think of an exception right now. Do you have anything in mind? Any exception scenario? 0 to 1 millisecond. Okay, I'll try. I'll see whether I have that question. Time quantity 0.3 units. So I'm opening my OneNote. Let me see if I have that. Okay, this one. Yeah, we'll try. We'll do that. So let me just create a space here. Okay, so just let me copy it here. So this one, if you reduce to 1 milliseconds, it will be very simple, nothing more. So here we were switching at an interval of 3 seconds. Now we'll switch at an interval of 1 second everything. Let me do it. So at 0 time instant, P1 is there. So so till P2 arrives, we can keep P1 running because there is nothing in the ready queue. So P1 will run till 2. When P2 arrives, it will switch. Then at 3 instant, and then P3 arrives, it will also switch. Now at time instant 4, basically, which one is in the first in the ready queue? P1 is first in the ready queue, so P1 will run for another 1 second, 1 unit of time. Then P2 will come till 6, and so on. You can continue this. So the response time, you can see the response time now, what is there. So P1 is 0, P2 is also 0, P2 has come at 2 and it has got the response at 2, and P3 is also has got immediate response. So it's a response, so it is 0 basically. Average response time is 0. So lower the response time, better it is. So you mentioned, I think you were basically mentioning when you say response time degree. So you can see that the response time has basically reduced. And if you see the turnaround time now, P1, so see if after P2 then P3 will come, then again P1 will come, then again P2 has run for 1, 2, so again P2 will run, then again P1 will run. P1 has run for 2, 3, 4. So again P1 will run. So you can see it is going to stretch as long as possible. So here P1 would be finishing at 13 and P2 would be finishing at probably 12 and P3 would be finishing as early as 8. But you can see now P3, all of them are going to finish longer. They will take longer time to finish. Then P2 will run, then P3 will run, and so on. So they are not going to finish earlier. So the average turnaround time is also going to be larger. P3 will be definitely greater than 8. P2 also I think has not finished till now. So I hope you got the idea. Should I complete it, or I think you can do the rest? So let us keep track how much it is done. P2, P3 is 1, 2, 3 and 4, 5. So P1 is still run and P2 has done 1, 2, 3 and 4. So P2 is finished. So now P3 will come. Oh, P3 was already 2. Okay, sorry. P3 needed only 2. So P3 would have finished earlier. So I didn't see that. So P3 CPU time was only 2 milliseconds. So P3 ran here and P3, okay, so here probably P3 finished earlier. So P1, P2, then P1, P2. Let me complete it and see. That can be an exception probably. So P1, P2, then again P1, then again P2. So P2 has taken 1, 2, 3, 4. So P2 will not come. So P1 is going to finish basically. P1 took 2, 3, 4, 5 and 6 and 7. Okay. So P1 will finish by 13. So in that sense now the average turnaround time P1 is 13, P2 finished at 9. So 9 minus 2. No, P2 finished at 11 minus 2 and P3 finished at 7 minus 3. So earlier what was the time? 13 plus 12 minus 2 and 7 minus 3. Okay, so here turnaround time is also decreasing. Yeah. So this is an exception for it. So in this case, turnaround time is not always increasing. But in general, what will happen? This is probably it's by luck it is happening. But in general, what will happen is, I hope you have got the intuition is thing that it will generally tend to stretch the process as long as possible because now they are switching earlier. So process may tend to finish towards the later side. And in that sense, turnaround time may increase in general. This probably is a scenario where uh, by the characteristic of the workload, it is still finishing early. So the turnaround time has decreased. Thanks for pointing that out. We'll just correct this statement on the record. Okay, so let me now continue to today's class. So in the last semester or in the last year, basically we had less time because the semester started late. So we skipped this topic in detail. We just introduced the idea of this proportional scheduling. But I think this semester we have time. So I'll just complete this scheduling algorithm. This is a third category or another family of approach. And this particularly I want to discuss because the current versions of Linux uses the scheduling algorithm which is based on this type of strategy. So let me just discuss this in detail more, and I'm going to use slide so that it is a little faster and it saves some time. So far we have seen schedulers which were designed to optimize performance in terms of response time and turnaround time. So the basic scheduling strategies were basically focusing on this, and we saw the best algorithm we saw in the last class was the multi-level feedback queue, which achieves both these goals in a more intelligent way. But it was not so trivial; it was a bit complicated, and implementations is not so straightforward, and it can be challenging to parameterize all this. So there are many parameters that you need to find the optimum value, and you to tune it to give a best performance may not be always possible, and it is also not so simple. And when the number of processes increase, it may not scale well. That is probably the third appropriation, may not scale well under load. So in general, in modern day systems, there can be as many as 1,000 processes running at a point of time, especially on data centers and all that. There can be huge number of processes, and to schedule all of them, the scheduler itself be very optimum, and should be able to scale up, so that it should not take a lot of time. If you time um, if you basically do a benchmark and time the amount of time taken by different modules of OS, you will find that scheduler does take significant amount of time, and so that will crumble if the load increases. If the number of processes increases, then scheduling time may increase. So it may not also scale well under load. So there can be are there any simple algorithms which are simple to implement, and which can scale well under load? And we'll see that strategy now. But that algorithm tries to focus on fairness instead of worrying about response time, turnaround times, and all that. It tries to be fair enough to processes, and in turn, indirectly, it will try to optimize response time also, and all that. We'll see that. But the main focus is fairness. It tries to be fair to processes. So what does fair scheduler basically mean? So the idea is simple. The basic idea behind all fair share scheduler strategies are like, every job will have certain weight or a priority, and those jobs will receive a share of the available resources in proportional to their weight. So in proportion to their priority, or in proportion to their importance, the job will get the percentage of the CPU. So the scheduling strategy tries to be fair in that manner. So it tries to guarantee that each jobs obtain a certain percentage of CPU time. There won't be starvation, and according to their weightage or priority, they will get their share of CPU. So it is not, as I said again, it is not optimized for turnaround and response time. So the idea of this fair share scheduler uh, began very early. So some of the early scheduling ideas, we'll first discuss them, because if we directly discuss the current modern day Linux scheduler, it will be a little difficult to understand straight away. So by discussing these simple strategies which came up a long back, it will also help us to understand the current day real scheduler which are there in the Linux operating system. So one of the earliest idea was lottery scheduling. The idea is very simple, and it is very easy to implement. So the basic concept says that you basically give processes certain number of tickets, and then you pick a random draw, just like people play lottery. You give them ticket numbers, and you pick up a random number, and whoever has that lottery number, he basically wins. So whoever process has that lottery value, that lottery ticket, he will schedule that particular process. um, so the percent of ticket represents the share of resource that the process should receive. So uh, the amount of tickets that you will give to each process will depend on its fate, on its share that each process should receive. So if it is a higher priority process, it will be given more tickets, and if it is a lower priority process, it will have a lesser number of tickets. So an example, let us say there are two processes A and B, So if A is a high priority process, and if you give 75 tickets to it, and B, if you give B 25 tickets, then this type of scheduling strategy will try to ensure that A will receive 75% of the CPU and B will receive 25% of the share of the CPU. And the way it is implemented is very simple. You basically just pick a random value and then schedule that particular, whichever process has that random ticket, you will schedule that to run. Let us take the same example. A and B has 75 tickets. So let us say there are total 100 tickets now. So 75 you give to A and 25 you give to B. So A will have tickets value from 0 to 74. So we start counting from 0 rather than 1. And then B will have from 75 to 99. So now you use a random number generator and pick up a random value from 0 to 99. And let us say these were the numbers that were generated. So accordingly, you will pick up the process. So 63 was with A, so A will be scheduled. Next time when scheduler has to make a decision, you pick up a number. Let us say it came 85. Then B will run and so on. So you can see now in this, I think there are around 15 to 16 draws. Out of that, B has run 4 times and A has run for the remaining number of times. So it's approximates the 25% share and 75% share. So in the short run, it may not approximate that exact share, but in the long run, because this is a probabilistic algorithm, so in the long run, the probability will become true. So it will achieve that percentage of share. Any question till this point? I hope the method was simple enough to understand. So what are the advantages of this type of, so if you implement this lottery mechanism through random draw, what are the advantages? So we can see that using this simple mechanism of lottery, we can automatically balance the share of the CPU time across processes. And it is lightweight, does not require anything basically about the process to store, unlike this MLFQ scheduling and all that, where we need to keep track of how the process has behaved in the past. Here we don't need to store anything about its past history or something, or what is the current state of the process and so on. You are not storing nothing about the process. You're just picking a random number and checking which process has that random number. So it is also very easy to implement. You no need to manage priority queues. So for MLFQ, you have to basically implement some kind of queuing data structures and all that, priority queues, data structure and all that. But here you don't need anything like that. And also you can avoid corner case behavior. So as I said, we have seen that there may be certain exceptions where a particular scheduling strategy may perform better or perform worse than what we may expect it to be. So in general, the general rule of thumb may go in one direction, but there may always be certain corner cases, certain exceptional workload which can perform too bad than what was expected out of it. And it is very difficult to handle all those corner case behavior. Otherwise, the implementation becomes very difficult if you try to handle all those corner case behavior. But here, this random algorithm, you don't find this. There is no corner case. There is no logic inbuilt. Basically, there is no complicated logic. So it also avoids any corner case behavior. So any exceptions are also avoided. And it can be quite fast. The scheduler can run very fast because whatever you have to do nothing but just call a pseudo random number generator, and as long as that function is fast, it can run very quickly. And also you can there can be many mechanisms inbuilt into this kind of ticketing by which you can change the priority or basically adjust the priority dynamically and so on. So you can give more or less tickets. You can do ticket transfer, inflation, etc. So for more details, I'm going to skipping this more detail. You can study from the book if you're interested in more details. So the only disadvantage with this random implementation is it's non-deterministic. So it may not deliver the exact right proportion in the short run. However, in the long run, it tends to be more deterministic. But in the short term, it can be non-deterministic. It can have a non-expected behavior also. So is the advantage and disadvantages okay with everybody? Okay, so implementation to implement this random scheduling lottery mechanism is also very easy. You may need nothing more than a simple list. So you can keep each job in the list, a node for each job. Let us say job A had 600 tickets, job B had 50 tickets, job C had 250 tickets. Now every time a scheduler has to make a decision to decide, you can run this code basically where you can keep a counter. Now generate a random number from 0 to total number of tickets. So here there are, I think, 150, so 250 and so 400. From 0 to the 399 you generate a random number, that is the winning ticket. Now you find which job has this winning ticket. So you start from the head node and traverse the node, and as you traverse the node, increment the counter by the value of the number of tickets each has. So counter equal to counter plus the number of tickets which are held by the current node. So first it will check A, so the counter will become 100. So let us say the winning ticket was 80. So if the counter value is 100 is now greater than the winner, you will break from this loop, and so wherever the current pointer is there, that job itself you will schedule. So A will itself will get scheduled here because A has that number. If not, let us say the winning ticket was 120. So since 100 is not still greater than 120, you will further move ahead in the list. You will go to the next job, get the counter value, and check in same way. So you will very easily find which job has the current ticket, and you will schedule that. So there is a comment on the chat window. Random is usually predictable due to seed. Isn't this a disadvantage? Yeah. So to generate complete random number, Gautam will get complicated. Yeah, that is a very good point. So that's why what we said here was basically, as long as you can generate a random number quickly, but if you have to really generate a real random number, then the algorithm will be very complicated and it may not be fast enough. So that's what I said, it's a pseudo random number generator, and due to seed, that can be a disadvantage too. So anyhow, what we are discussing is we don't use, none of the modern day scheduler use this random strategy. We'll see why. We'll see if there are better techniques available, but just to start with, we just wanted to enumerate all the advantages with as simple algorithm as just this random picking of lottery. But yeah, details, if you go to more details in the implementations, there can be issues, as we have basically pointed out, that real random number generation is not an easy algorithm. If you study in data set in algorithm course, it's an NP problem, and so NP hard problem, so it's not so easy, so it cannot be done very fast. But pseudo random generator can done fast enough, and as long as you are okay with, you don't want to guarantee total randomness, you can it can be acceptable. So more details of ticket mechanism, like there are currency, you can adjust currencies within a process, within a user, all that. There can be way to transfer tickets, there can be way to boost the tickets values, temporarily raise or lower the number of tickets, and this you can study from the book. I am going to skip it. It's not important because, as I said, we are not going to implement this random one. We'll discuss in more detail the one which is actually there in the modern day scheduler. This is just also an empirical study of how fair this random algorithm works. So if you use a matrix called unfairness, so this unfairness is basically the time taken by the first job to complete. first job, the time taken by the first job to complete, and the time taken by the second job to complete. If you divide by that and you take that as an unfairness matrix, so let us say there are two jobs, both have the same number of tickets, so both should ideally finish at almost the same time. So in that case, this unfairness matrix should be equal to 1 or near 1 value. So if the algorithm is fair enough, then this algorithm should reach 1 value. But you can see when the job length are small in shorter time scales, the unfairness can be quite huge. Instead of value 1, it can be from 0.5 to and so on. So the first job may finish as almost double the time. The second job may take almost double time than the first job. So empirically that is found there. But when you increase the job length, then this random algorithm approaches this ideal fairness value. So that is the disadvantage. We have seen that for shorter jobs, probably this random number generation will not work. It will not be fair enough. It may not be completely fair, but as long as you are okay with reasonable degree of fairness, you can go ahead. But if you want to avoid this randomness, if you want to make a deterministic fair scheduler, there is also a simpler way to do that. The method is called stride scheduling. So instead of doing a random number generation, you calculate, you still give each process some number of tickets, but now each process will have a different stride value by which you will advance its counter value. So we'll keep track of counter for each process, and we'll increase that counter value by certain stride value, and that stride value will depend on the number of tickets that each process has been given. So that stride value can be calculated by dividing a very big number with the number of tickets that the process has been assigned. So let us say the same example, A has 100 tickets, B has 50 tickets, and C has 250 tickets. So the stride for A can be calculated. You can choose a very big number, let us say 10,000. Then the stride for A will be 10,000 divided by 100, which is 100. For B will be 200, and for C will be 40. So now you will keep track of a count value, let us say a pass value for each process. And whenever a process runs, you will increment that pass value for that process by its stride value. And every time the scheduler has to make a decision which process has to run, it will see which process has the lowest pass value. So whichever has the lowest pass value, it will schedule that one to run. So let us see how it works. So the same example, we calculated the stride value of A was 100, for B it was 200, and for C was 40. So initially the pass value for everybody will be initialized to 0. Now scheduler decides which one has to run. It can pick any one. Let us say it pick the A first one. Now A ran, A's pass value increment will be incremented by its stride. It will become 100. Now the next time, so it has to decide. It will decide among B and C. Both have 0 value. So let us say it decided B. So B's pass value will be incremented to 200 now, and C still remains 0. Next time when it has to decide, C will run, and C will be incremented by 240 by 40. So now next time when decision has to make, which one has the lowest? C has the lowest, so C will be chosen. So C will become 80, then again C will be chosen. C will become 120 here. Now once we become 120, now the A has the lower thing, so A will be scheduled first, and so on. So if you run this, we have not completed the table. You will find that this will exactly deterministically approach the exact percentage of share that each process reserved based on its number of tickets. And the implementation is also easy enough. You have to maintain a queue, a main queue. You can use a heap or something like this. To decide which one has the lower pass value, you just remove from that queue and get the current process that has to be scheduled, and schedule that one, and increment the pass value of that current process by its stride, and then insert that current process into the queue again. So you can make a min heap or something like that. So that kind of thing can be done. And as we can see that they will run in exact proportion to their share of tickets. So A will A had 25% of share, B had 12.5% of share, and C had 62.5% share. So if you see the number of times it ran out of total things, you will find that this proportion is will be adhered to even on shorter time scales. So any question till this point? Is this tight scheduling clear? So there are some issues. So you may then say, then we should never use lottery algorithm because tied scheduling is deterministic. Why would ever anybody go for random lottery? There are disadvantages of tied scheduling also, because here we need to store a lot more state than we needed for a random lottery algorithm. We didn't need to store any thing about the state of process. Here you need to keep track of the counter value, the pass value, and the stride value of each process. And also there are issues that may happen in stride scheduler. For example, let us say a new process comes, then its pass value will be 0. So in the previous example, let us say at this point of time, let us say a new process came D. So its pass value will be 0. So for next 3 or 4 times, probably D is going to be scheduled always till its pass value catches up to one of these lower values. So it can tend to monopolize the CPU for some point of time. Another process will have to wait, so it can affect the interactiveness of the other process and so on. So there are ways to deal with this also. You can, for example, Linux scheduler, what it does basically, we'll see how it does. Basically, whenever a new process again, let us say we'll talk about that when we come to that. There are ways to handle this also, but these are some disadvantages of stride scheduling, and lottery algorithm did not have these issues. Whenever a new process comes also, there is no problem. You just have to pick up a random number and see which one of whether the new process or the older process has the random number. So that has its own advantages, and as we have seen, none of the scheduler is a panacea. Everyone has its own pros and cons, and you have to basically pick up based on your requirements. But one issues which are common to both these lottery scheduler and stride scheduler is that how do you know how many tickets to give to each process? Because that is based on which until unless you decide how many tickets to give to each process, you cannot run these algorithms. And how do you decide? How do you know judge the importance of a process or the priority of the process? So MLFQ did it intelligently by seeing how it behaved, and it adjusted accordingly and so on. But here, how do you do that? So this is an open problem, but fortunately it is not a major problem in many domains. For instance, if you are doing it in a cloud computing, in a data center server or a cloud, here you can know, basically based on the external criteria also, you can decide the tickets or the priority of process. So the user which pays more for the services, he gets more number of tickets. That is one simpler criteria. And other kind of things can be there. So for certain customized scenarios, this may not be a problem, but a general purpose solution to do this ticket assignment is still an open problem which needs to be solved. We'll see how basically the Linux scheduler does this. Okay. So let us come to the case study. We don't have a lot of time, so let us talk about some of the modern day Linux schedulers. So again, most of the discussions we are going to do in terms of using Linux, because Linux is an open source and most of the textbooks talk about Linux things. But it will be a good reading exercise for all of you to see what are the other OS like Windows OS and Mac OS. Of course, Mac OS is kind of a version of a Unix and Linux only, but yeah, it has many changes and all that. So it's a reading exercise for all of you to basically explore what are the scheduling algorithms or any concept that we discuss. what these other OSs basically use. Okay, so Linux scheduler used a scheduler which was called O1 scheduler till the version 2.6.23, and it is nothing but it's a kind of a version of this MLFQ only. So Unix scheduler used strictly this MLFQ. This Linux scheduler just had a modification of this MLFQ version. So it had certain 140 priority levels. Now each priority level had two queues. So instead of just one queue, there were two separate queues for active and inactive process. So the process which goes for sleep or go for an IO or and all that, you keep them on inactive queue, and other you keep on an active queue, and so on. And then again, there were ways to change the process priority over time. So similar rules like MLFQ would apply for that purpose. And of course, we will schedule those with the highest priority. So those priority levels which are higher will be done. And interactivity was the main focus. So mostly all of these priority levels will run round robin with within each priority level with certain time quanta, so that you have a good interactive performance for each scheduler. But this is now no more used. It was used only till these things, and there are some again there was some waiting mechanism also there, but I'm not skipping about that. The one which is used in the after this 2.6.23 is called completely fair scheduler, and this is basically the version of this fair scheduling that we have discussed in this class. It uses instead of this MLFQ, it moves to the fair scheduler strategy, and it is very similar to stride scheduling algorithm that we discussed. It basically keeps track of how much process has run and increments that based on its stride, and we'll see about that. So it's very similar to stride scheduling, and but it behaves a bit like weighted round robin algorithm, and with dynamic time slices. So instead of a static time slice, the time slice for will also dynamically get adjusted depending on the number of processes, the load on the system. If there are only few processes in the system, it will have a larger time slice, but if there are more number of processes on the system, the time slice will reduce. So that's why it's built to scale and perform well under load. So it is particularly targeted. It uses some good data structures so that it can perform well even if there are as large as thousands or lakhs of processes running on the system. So the processes are ordered by the amount of the CPU time they use. So we'll talk about that in the next slide. So instead of queues, basically instead of normal priority queues, it uses some very efficient data structures to ensure that it has log-in runtime performance. So while deciding which is the next process to run, it will ensure that it has log-in complexity. So we'll talk about the efficient data structure also, which one it uses. But the name is slightly confusing. It says completely fair scheduler, but it isn't actually a completely fair scheduler. It does not guarantee deterministically fairness as would happen in a normal stride scheduling algorithm. But unfairness is bounded more or less for on a smaller time window. It will the fairness may not be exactly completely fair, but as the window you increase, the fairness is guaranteed. So the unfairness is there is a short bound on that. Again, for more details, you may have to read on the book. I want to avoid going to more details. Just giving you the basic idea about this modern day schedulers. Most of the books avoid these things. They only discuss the old methods. But in Professor MG's book, at least they have discussed this fair scheduler to a certain extent. So I thought it will be good to discuss here. So this CFS basically keeps track of something called virtual runtime. So each process, whenever it runs, it accumulates its virtual runtime. So so the counter that each process is keep track of is this virtual runtime, and the CFS picks whichever process has the least virtual runtime. So whichever has run the least number of time, basically it will schedule that process to run. And as we said that it varies the time slice dynamically, and to do that basically it uses certain control parameters, like it uses a parameter called schedule latency. So let us say the schedule latency value is 48. Typically it keeps 48 by default, 48 milliseconds. And if there are, let us say, the number of processes are 4, then the time slice which is basically decided will be, you divide this schedule latency by the value of n. So the time slice that will be 48 divided by 4, which will be 12 milliseconds. So each process will run in a round robin fashion for 12 milliseconds before switching. But if the number of processes are, let us say, reduced to 2 now, the time slice will increase. Time slice will become 24 milliseconds. So in that way, it adjusts the time slice dynamically so that the performance is optimized. Because too often switching will have an overhead. We have seen round robin has this problem of context switching and all that. So if you reduce the times contract too often, then if you switch too often, then that has a problem. So to balance that, the time slice is adjusted dynamically, and there is a minimum granularity. So if this number of processes increase too much, this time contract can decrease to a very low value, and that can also lead to an overhead. So there is a minimum granularity level, let us say 6 milliseconds. So if the time slice decreases be lesser than this 6 milliseconds, it won't go for that. It will keep it will keep the time slice fixed at 6 milliseconds, so that it won't switch lesser before 6 milliseconds. So in that way it controls the switching thing. And normally these are all multiple of your normal default system timer. So system timer may have, let us say, be programmed at 1 millisecond or 2 milliseconds. These all values will be multiple of that, because you will need, the scheduler can only come into action, will spring into action when there is a hardware interrupt. So it has to be multiple of those. And priorities are adjusted through some kind of a weighting mechanism. So there are some values you can give to each process. So in this scheduler, the term is used called nice value. So how nice the process is, based on that you give its value. So the value ranges from -20 to 19. So default value is 0. If you don't want to give any priority, higher or lower, the default value is 0. If you want to give a higher value, you have to give it a negative value. So negative implies higher value and positive implies lower priority. So if you're too nice, probably you don't get that much attention. If you are more demanding, you get more attention. So that is, I think, why negative value implies higher priority. Okay, so and this weighting is also used for many things. It is used for time slice calculation for each process. So now you can adjust the time slice for each process. Instead of having a fixed time slice for each process, you can adjust this time slice with the weight of each process. So that can also be done. The detail how the formula for this in the book you can read. Similarly, it can also update the accumulation of virtual runtime also depending on the weight. So sorry for that interruption. Somebody's car has, I think, alarm has switched off, gone off. I hope you are able to hear me. So this virtual runtime is also, instead of accumulating in the straightforward way, it gets updated in a weighted manner. So that through that the higher priority process will get more share and lower priority process will get lesser share. So that is way it is done. And the efficient data structure that I was talking about, it uses a red-black tree, because as you would have studied in your data structure, it's a balanced tree. The normal binary search tree and other things have a corner case behavior. If the performance can degenerate sometimes from log n to O of n when you have to schedule or search a process with a minimum value. But this red-black tree ensures that the tree remains balanced. So it maintains the list of active processes on the red-black tree, and generally it has high efficiency and scalability. So even if you increase the number of processes, you can always guarantee that it will have a log n performance. and I hope you understand that. So the virtual runtime of each process, these are, let us say, virtual runtime of each process. So you arrange the processes based on the virtual runtime on this red black tree, and only the running processes are kept. So those who went for IO or sleep and all that, they are tracked somewhere else. They are not put on this thing. And whenever you have to basically pick the next job to run, the leftmost process is always so you get in O1 time basically the leftmost process, and is the least. This will have the least virtual runtime. It will be scheduled next, and then its virtual runtime will increase. Then you have to again reinsert it into the red black tree, and then you have to rebalance the tree. So the balanced tree will get balanced, and then again you will always find the minimum things. So while making a decision, this will be very quick, and then once it has made a decision, this adjusting can happen in the background basically later on also. So the decision can be done very quickly using this, and it always guarantees that the the, the the performance will not degenerate to worse cases. And let us say if a job wake up after a long sleep or of an IO, then again, as we have said in this stride scheduling, it can monopolize because it will have a zero virtual runtime or a very low virtual runtime, and then more of it may get it can monopolize. So to avoid that, this CFS sets the virtual runtime of that job to the minimum value found in the tree. So whatever is the minimum value, it will set that it will adjust the virtual runtime of that job to that minimum value. So in order to avoid monopolizing the that job to get the CPU for the next few decisions. So that is the way. Of course, that has also a trade-off. That has a problem, but that is the way this CFS does. And there are the other interesting stuff about CFS. I have not put it here. You can read from the book more details.